why don't we take a look at something involving group by? We'll step away from problems involving correctness, and we'll talk a little bit about problems involving speed and performance. Let's take a look. I want to talk about a very simple thing that pandas makes a little bit hard, and in fact makes maybe a little bit unnecessarily hard, but which gives us some guidance for how to use pandas a little bit more effectively and things that we should do that unfortunately a lot of people don't really seem to do very often. Here's the scenario. I have some code, and that code is working with some data, and what exactly that data represents maybe doesn't matter that much. So I have some information, it has some categories, I have some values, and I have some weights associated with each one of these entries. The categories may not be unique. That is to say, there might be some entity and then some categorization associated with it, but I'm not going to represent the entity identifier, the unique identifier. I'm just going to represent the categorical identifier. And so what I want to do, if I have something that can be assigned to categories with a value and a weight, is I often want to say, what does the weighted mean? I want to do a grouped weighted statistic. And so, for the most part, the data is pretty straightforward. Just some random values, just some normally distributed weights that are always positive. And all I need to do is make use of the group by mechanism in pandas. I'll group by the category, and I'll do a dot apply. I'll take the value and multiply times the weight and sum it up across the whole group. I'll take just the value of the weight and sum that up across the whole group, and I'll divide them, and I'll get a grouped weighted summary statistic. And here is my result. Everything seems to work pretty well. So can you spot what kind of sucks about this code? And I'll give you a big hint. The answer is not that dot apply is slow because it calls a Python function on every row of a data frame or a series. That is only the case with dot apply on the series object. Dot apply on a group by will call a Python function once per individual group, so once per category. And in this particular case, when we look at the number of categories we have 10 unique categories, so it's going to call a Python function 10 times. Maybe that's not the end of the world. I'll give you another hint. Dot apply is a bad idea, but it's not a bad idea for the same reason that dot apply is a bad idea. In other words, dot apply on group by is a bad idea for a completely different reason that dot apply on a series object. But they're both bad ideas, and they're both hot spots for performance issues. Can you spot what kind of sucks about this code? Well, if you said that what I should really be doing whenever I want to do some sort of group by analysis is figure out how to rewrite that group by apply, if it needs to be something that looks on two columns, into a sequence of operations involving at most group by transform and group by ag. And let's do one thing here. There we go. You're absolutely right. It turns out that, and I think this is libs here where some of these extra libraries are located. It turns out that when we have a group by apply, it oftentimes is going to be not only slow, but very, very, very slow. And it turns out that even if we are to engage in certain contortions like rewriting that in terms of a group by transform and a group by sum and multiple individual column computations, this ends up being significantly faster. Now, here in this code, there's also the use of some additional things, and we'll take a look at those in just a moment. But, I made the case for you. And the case that I made was that this is slow. So let's really take a look at what's most interesting here, not the specific example, but the explanation. Let's take a look at what I mean by slow. And so I'll show you a couple of different ways that we can perform a grouped summary computation. Here is group by apply. And just to make the slowness of this code a little bit more visible, I'm going to increase two things. I'm going to increase the total amount of data we have to 100,000 rows, and increase the number of groups we have to 10,000 groups. Now, bear in mind that what I'm going to show you is going to be very sensitive to the cardinality of this grouping. In other words, if I only have, say, 3 groups, we're not really going to see a big difference. But if I have a relatively large number of independent groups in relation to the total amount of data I have, and I have a relatively large amount of data, we will see a difference. For this 100,000 rows with 10,000 unique groups, it takes 2.6 seconds to do a group by apply. Why? Remember, when we do a grouping operation in pandas using the group by mechanism, we have a couple of things that we can do after the group by on that group by object. We can run built-in functions. We can do a group by filter, which I guess it only makes sense if we want to filter it. Or if we want to do a computation, we can group by ag, transform, or apply. Group by ag basically means we want to take the original data, identify what the groups are, and for each individual group, we want to have one resulting row. We want to aggregate that. So the resulting data frame will be smaller than the original data frame, or same size or smaller than the original data frame, and we know exactly how large the resulting data frame is going to be. One row in the result for each individual group that we have. We know what the indexing of the resulting data frame will be. It'll be exactly on what the groups are. And as a consequence of all of those things, we can pre-allocate the resulting data frame and just fill it in. We can say, these are the groups, pre-allocate, allocate once, and then fill in. For a group by transform, what we're going to do is we're going to say, well, the result of a group by transform is always the same size and the same indexing as the original input data frame. So when we do a group by transform, we can pre-allocate that result. And we know exactly what it looks like. Same number of rows as the input, and the indexing will be identical to the input. But group by apply says we have no known relationship between the input data frame and the output data frame in terms of what the indexing is going to be or in terms of how large it's going to be. And as a consequence, group by apply cannot pre-allocate one resulting data frame. It has to allocate each individual intermediary result and then concatenate them together. And this ends up being very slow. The slowness of this is not related to the use of that Python user-defined function on each individual group, because we'll see the same slowness. We should see the same slowdown if we were to do a group by ag or a group by transform. And yet, we'll see that the group by apply in a similar case to a group by ag or transform will be markedly slower as just a consequence of that inability to pre-allocate and the concatenation. On the other hand, a group by ag and a group by transform cannot look at more than one column at a time. So if we were doing some sort of weighted analysis, well, we got the values here and the weights here. We cannot look at them at the same time in a group by ag or group by transform. So apply seems to be the only option that we have. In general, even when apply is the only clean option that we have, the slowness of it is so severe that we might actually want to figure out how to force a group by ag or transform to do the same analysis by breaking down the computation into intermediate steps until you can get it down to a step that operates on just one column at a time. Let me show you what that would look like in this case. We'll first create a brand new column with the total weight. Then we'll create a column with the weighted value, combining the column from the above with the value and the weights. And these can be done down the entire data frame without anything more than just one additional group by ag here. And then we'll do a group by at the end. So we'll take this one singular group by and we'll turn it into 2 group bys. And you'll say, well, 1 group by? How can that be slower than 2 group bys? You must mean 2% slower. No, look at this. This is ridiculous. 2 seconds versus 0.08 seconds. This is more than 10 times faster than the group by apply. Group by apply is very, very slow. Now, if you're curious, the result of these will be identical. There is no difference in the actual resulting value, except, of course, if these are floating point values, we'll have to deal with that there might be some differences from the order in which operations are being performed, since a floating point math is neither associative nor commutative. But for the most part, insofar as we assume some noise from any operation that works with floating point, we'll see that these will tie out. In fact, it turns out that reformulating this as a group by ag or a group by in multiple steps is not the fastest we can make this. we could, for example, say, you know what, all group by is doing, if the data is sorted already, is it's going to sort the data. If the store does not say it already, it's just going to figure out where the boundaries of the groups are, and then it's just going to take each group from its starting point to its ending point, and then perform an operation in that. And I can kind of do that in NumPy by creating masks or by doing some kind of fancy indexing. I could use NumPy on the raw data to figure out where the boundaries of the groups are. That actually is a very easy thing to do if the data is sorted. All I have to do is compare the value against the values shifted, the grouping values against values shifted. I could then take that result and create some indexing in NumPy that just indexes out from the starting location to the end location and applies the operation. Because I can do this in NumPy, I have a little bit more flexibility to operate on multiple columns at a time. So I could first identify the boundary locations, and then with a regular old for loop over the starting and stopping point for each of those, and just perform operations on views of this NumPy ND array, taking a look at the two columns, which have also been extracted to just their NumPy values. And you might say, that's a lot of steps. Surely that can't be faster than just one group by. And yet, it is. And not just a little bit faster. Well, actually here in this case, it's about the same speed as this. Hold on a second. I'm gonna blow your mind in just a moment. Let's maybe increase the cardinality here, and we'll see a little bit more of a difference. Oh, and this gets a little bit too much if we increase this. So let's maybe increase the total size of the data a little bit. Although that might slow down our group by apply too much. So here we'll turn off the group by apply and just look at the group by ag versus our grouped weighted mean here. You can see here, okay, maybe not a big deal. That's like 2% faster. But if we take that exact same code and we just lower it down into Python and just add one tiny piece here, we tell Python to not do boundary checking on this, to say here's the boundaries of where the array begins and ends, but otherwise don't do any sort of out-of-bounds checking, just do raw access to the underlying NumPy and D array. So they're just views of this thing. And we write just a little bit more code and really, really dumb, simple C code and just compile this thing. We end up seeing that there are significant additional performance improvements that we can get. Look at that. We now reduce this by yet another order of magnitude. We can, in fact, make this code almost 100 times faster by taking a regular group by apply and just decomposing it into some Python code that looks at where the boundaries are and then looks at views of the underlying NumPy data from the starting point of the boundary to the ending point of the boundary. Grouped weighted summary statistics end up being one of these things that pandas the group by API is just not well suited to do. And it turns out that things that you would otherwise anticipate being so contorted or so many simple steps, how could they be faster, end up being remarkably faster. In general, these approaches I think are actually worthwhile because 100 times speed up I think is worth a lot. That's the difference between something taking, say, 10 hours and something taking, say, only a couple of minutes. That means a lot in my day-to-day life. But in general, what I want to get from this and the guidance that I want to bring to the code that I write is, number one, we want to avoid group by apply wherever possible. And oftentimes, avoiding group by apply with just a little bit of contortions is worth the weight of the contortion because the speed up that we will see will be significant in the order of one order of magnitude or more. And two, it's often the case that we might actually want to write our own mechanics, our own utils on top of pandas, because you could say, if you can make group by weighted mean so much faster with some Python code, why didn't the pandas core developers do that? Well, of course, the pandas core developers are writing for a very general audience, and there are assumptions that I'm making here that will not be applicable to the kinds of problems that people might want to use this kind of code to do. But if I'm writing this for myself, I can very comfortably make those assumptions, and I can very comfortably benefit from these speedups. One thing that I very rarely see people who are heavy pandas users do is create their own additional utility libraries that they take from project to project around pandas that allow them to find these narrow fast paths and speed up and to write them out in places in ways where, maybe I just have to write this once and use it forever. And for 100 times speed up, I don't usually like writing anything that's close to C, but I'm willing to write 20 lines of Python code, especially if I can put it into a util library and carry it from project to project.